If you ever have to share a pizza, just cut it into 15 slices. Let me explain. This is a pizza to be shared by Alice and Bob. Bob will cut the pizza into any number of slices. The slices can be different sizes. Each cut is a straight line from the center to the crust. Since Bob did the cutting, Alice will choose the first slice. Maybe this slice. I wrote A1 because it's Alice's first slice. Removing this slice creates a gap in the pizza. Now it's Bob's turn. Can he choose this slice? No, that would violate the code of pizza. From now on, every slice must be adjacent to the gap, maybe to keep the pizza hot. So Bob must choose this slice or this one. Suppose he takes this one. Now it's Alice's turn, then Bob's, back and forth until the pizza is gone. Both players want as much pizza as possible. They're not exactly friends, more like frenemies. If both of them play perfectly, who gets more pizza? Bob because he cuts the pizza, or Alice because she chooses the first slice? The answer may surprise you. It involves an intriguing, subtle strategy. Mathematicians have studied this game for decades. The full answer wasn't known until recently. In this video, we'll solve the pizza game. For each number of slices, we'll see who has the advantage and by how much. Are you ready? Are you hungry for the answer? Let's go. To start, suppose Bob cuts the pizza into 6 slices. He can make the slices as big or as small as he likes. I've written the angle measures. Alice chooses the first slice. What strategy should she use? One idea is to always choose the biggest slice she can. That's called the greedy algorithm. For example, she can choose the 90-degree slice. Say Bob goes here. Alice's biggest choice now is 40 degrees. Maybe Bob goes here. Then Alice chooses the other 40-degree slice. Bob takes the last slice. Altogether, Alice got only 170 degrees, while Bob got 190. So, greed is not always good. Does Alice have a better strategy? Yes. Let's start over. Label the slices odd and even in an alternating pattern. Here, O stands for odd and E for even. Alice will look at which has more, the odd slices or the even ones. Here, the odd slices have more. So Alice will choose any odd slice, say this one. Then Bob chooses. His only choices are even. From now on, Alice will choose the slice adjacent to Bob's previous slice. That will be an odd slice, back and forth until the pizza disappears. Alice got all the odd slices, so with foresight, she got at least half the pizza. That was for 6 slices. Does that strategy work for other numbers? Yes. As long as the number of slices is even, Alice can get at least half the pizza. This result reminds me of a classic coin puzzle we'll need later. It sometimes appears in job interviews at technology companies. Suppose we have 6 coins in a row. Each coin has a value. In each move, a player takes a coin from one of the ends. Alice goes first. Maybe she removes the 74. Then it's Bob's turn to choose from an end. Maybe the 67. Back and forth until all the coins have been taken. Adding up, we see that Alice lost. Could she have won? Yes. Let's start over. You may have figured out that we can again mark the coins odd and even. Here the coins in the odd positions add up to more than the coins in the even positions. So Alice will claim all the coins in the odd positions. Bob can't stop her. He'll be stuck with the coins in the even positions. So Alice will win. The same works whenever the number of coins is even. Alice gets at least as much value as Bob. We'll use that coin result later. Going back to the pizza game, we showed that if the number of slices is even, then Alice gets at least half the pizza. But what if there were an odd number of slices? The odd case looks even better for Alice. For example, with 7 slices, Alice will get 4 slices and Bob will get only 3. There's no way Bob can get more pizza, right? Wrong. Bob can cut the pizza into an odd number of slices and get more than half the pizza. Here's an intriguing example where he cuts the pizza into 15 slices. I've labeled each slice with a number to mark how big the slice is, say its area. 2 comments. First, some of the slices are of size 0. If you don't like size 0, just make them tiny slices, such as 0.001. Second, because we couldn't actually see a slice of size 0, I've drawn the 0 slices bigger than they should be. Here's another way to visualize this pizza. We'll use pepperoni chunks to mark how big each slice is. Each slice has 0, 1, or 2 pepperonis to indicate its size. There are 9 pepperonis in total. Alice and Bob are trying to get as many pepperonis as possible. I claim that Bob can always get at least 5 of the 9 pepperonis. Even though Alice will get more slices, Bob will get more pizza. Alice has 15 choices for her first slice. Let's say she chooses a 0 slice, maybe this one. There are 2 slices next to it. Imagine we straighten out the pizza with those 2 slices at each end of a row of slices. We have 14 slices in a row, just like 14 coins in a row. We can split those 14 slices into alternating odd and even slices. Bob will choose odd or even, depending on which has more pepperoni. Here are the slices Bob will choose. Bob will get at least half the pepperoni. Since there are 9 pepperonis, Bob will get at least 4.5. But these pepperonis don't come in fractions, so that means Bob will get at least 5 pepperonis. Alice will get at most 4. That works if Alice chooses a 0 slice. There are 6 other slices that Alice can choose first. We'll deal with 3 of those slices next. Here they are. In each of these cases, Bob can do an odd-even split to get 5 pepperonis. There are 3 remaining choices for Alice. Here they are. In each case, here's the slice that Bob should choose first. It turns out, and I encourage you to pause the video and check, that no matter how Alice continues, Bob can secure 5 pepperonis. So, here's a recap. Bob can cut the pizza into 15 specific slices so that Alice gets at most 4/9 of the pizza. Bob gets more than half. But can he get a lot more? Can he take 70%, 80%? What do you think? It turns out the answer is no. Alice can always get at least 1/3 of the pizza, no matter how Bob cuts. We already know this when the number of slices is even, so from now on, suppose the number of slices is odd. We can assume that Bob will play his optimal strategy, the one that maximizes his final amount of pizza. We'll create a strategy for Alice that guarantees at least 1/3 of the pizza. The hard part will be to figure out which slice she should start with. Alice will first do a thought experiment. She'll start with any slice, say this one. For her remaining choices, she'll always take the slice next to the one that Bob just chose. We'll call that the follow Bob strategy. For example, Bob's best first choice might be this slice. Then Alice will choose to take the one next to his. Then Bob might take this slice, so Alice will follow him, back and forth. So far we have an alternating pattern between Alice and Bob, but at the end the pattern breaks, since there are an odd number of slices. Now it may happen that Alice already has more than 1/3 of the pizza. If so, great for her. Unfortunately, that didn't happen here. Alice has at most 1/3, Bob has at least 2/3. But remember, this was just a thought experiment. Alice would love to have all the slices that Bob currently has. She'll find a way to get halfway toward that goal. Alice will use this picture to figure out which slice she should have started with. As I mentioned earlier, the slices alternate between Alice and Bob with one exception. I'll draw a divider at the exception. Starting from the divider, imagine going around the pizza until we see exactly half of Bob's pizza. We get a second divider here. The 2 dividers split the pizza into 2 sectors. In each sector, the slices perfectly alternate. Bob has the same amount of pizza in each sector. Since he has at least 2/3 of the pizza, his portion in each sector is at least 1/3 of the whole pizza. Let me draw this pizza again. The pizza on the left is the thought experiment. The pizza on the right is the real one. So, which slice should Alice start with? She'll steal one of Bob's slices from the thought experiment, the slice that contains the second divider, like this. From now on, she'll follow Bob as before. With the follow Bob strategy, the slices alternate with one exception. The exception will depend on Bob's choices. For example, at the end, the pizza might look like this. The break in the alternation is in the left sector. Therefore, in the right sector, Alice has all the slices that Bob used to have. So, she has at least 1/3 of the pizza. Here's another such case. The pattern break is still in the left sector, so in the right sector, Alice still has at least a third of the pizza. On the other hand, the break in the alternation could be in the right sector, like this. In that case, in the left sector, Alice has all the slices that Bob used to have, so again she has at least a third of the pizza. Here are two more such cases. The pattern break is in the right sector, so Alice does well in the left sector. To recap, in every case, Alice gets at least a third of the pizza. But that raises another question. Could Alice guarantee getting more than a third? What do you think? It turns out the answer is yes. She can always get at least 4/9 of the pizza. 4/9 was the exact answer we got for 15 specific slices, so that's the most Alice can hope for in general. The result that Alice can get at least 4/9 of the pizza was proved in two papers from 2008. One paper has these 3 authors. The other paper has these 5 authors. The proof of the 4/9 bound is complicated, so I won't give it here. The key idea is for Alice to mostly use the follow Bob strategy, but to allow 1 or 2 exceptions. I'll include links to the papers in the video description. Let's summarize the main results for a fixed number of slices. Suppose that Alice and Bob play perfectly. If the number of slices is even, then each gets half the pizza. After all, we already showed that Alice gets at least half the pizza, while Bob can make each slice the same size. As a trivial case, if the whole pizza is just one big slice, then of course the first player, Alice, will get the entire pizza. But if the number of slices is a small odd number, from 3 to 13, then it turns out with optimal play that Alice and Bob will each get half the pizza. This result is not easy to prove, but explains why we need an example with 15 slices. Finally, if the number of slices is a big odd number, 15 or more, then with optimal play, Alice will get 4/9 of the pizza and Bob will get 5/9. So, if you ever have to share a pizza, just cut it into 15 carefully measured slices. See? Math is practical. If you like this video, check out this other one too. Thanks for watching!